Hello everyone, welcome to Analog Electronic Circuits, lecture number 13. So today we are going to start about a new topic, that is a need of multi-stage amplifiers. So let's begin and understand why there is a need of studying the multi-stage amplifiers. So basically the voltage gain obtained from a single stage amplifiers is limited. So what are the various single stage amplifiers which we know so far? So let us list that list them down. So in the first category, we have discussed about BJT amplifiers. Okay. So BJT amplifiers. In BJT amplifiers, we have studied three types, right? We have studied common emitter amplifier. Then we have studied common collector and common base. So out of this, the common base and common emitter will provide a voltage gain of around, let's say, close to 200. Voltage gain of around close to 200, whereas common collector will provide a gain close to which is around 1. Okay, so the gain of the single stage amplifier is limited. Also we have studied the MOSFET amplifiers. So second category we have studied of single stage amplifier will be MOSFET or JFET amplifiers. Now here also we have studied three configurations, namely common source, common gate, let me write it down, common source, common gate, and common drain. So out of this also the common source amplifier will provide a gain of max from 10 to 15. Okay. Similarly with the, we have common gate and common drain amplifier also. So out of that we have a common drain. So in this case, common gate also will provide a gain suitably around, let's say, so common gate amplifier will also provide a gain of 10 to 15, whereas a common drain amplifier will provide a gain of around 1, close to 1. So as you can see, these are the voltage gain which are associated with single stage amplifiers, and they are quite limited. So that's why we require cascading. So cascading, what it will do is it will increase the voltage gain, and it might also improve the input and output impedance of the entire circuit. So that's the motivation to study the multi-stage amplifier. So let's see, here we have seen, here we see over here N-stage cascaded amplifier. Cascaded means connected one after the other. So this is my stage 1 providing a gain of AV1. This followed by stage 2 providing a gain of AV2. And in say similar manner, we can have stage N providing a gain of AVN. Now here we have applied input. Here R in 1 is my input impedance, input resistance of the first stage. R out 1 is my output resistance of the first stage. Similarly, R in 2 is my input impedance of the second stage. R out 2 is the output impedance of the second stage. R in N is the input impedance of the N stage. And R out N is the output impedance of the output resistance of the N stage, right? So this is my N stage cascaded amplifier. So if you want to find the overall resistance of a cascaded amplifier, so remember this is a concept over here which we are studying. The overall input resistance of a cascaded amplifier is equal to the input resistance of the first stage, right? So let's say if you have a chain of, two cascade amplifiers, which are, two amplifiers which are connected in cascade, right? And you're supposed to find the input resistance of the entire cascade stage. So the input resistance of the entire cascade stage will be Rn, which is equal to the input impedance of the first stage, right? So don't forget this rule. This is very, very important, right? Let me put it inside the box. Yeah, this is an important rule. And this is the first concept which we have studied. Okay. Now next, if I want to find the output resistance of a cascaded stage, so it says that the overall output resistance of a cascaded amplifier is equal to the output resistance of the last stage. Okay. So your R out overall will be equal to the R out of the last stage. And here the last stage is nth stage. So that's why this is also another important concept which you have to remember, that the output resistance of a cascaded stage will be equal to the output resistance of the last stage. Okay. So here we could have elaborated a little more. Let me just do that. Okay. Instead of writing Rn, I can write it as Rn of first stage. Okay. And here I can write it as R out is equal to R out of last stage. So y'all can also note it down in your books that Rn is equal to Rn of the first stage in a cascaded network, and R out is R out of the last stage in a cascaded network. Okay. So these two important concepts are there for the cascaded amplifier. I hope that you have noted down. Now, let's check about that how the cascading will affect the gain. So again, we consider the end stage cascaded amplifier. Now let's say that amplifiers over here, there are around one, stage two, and stage n. Let's say that the amplifiers will have individual voltage gain as AV1, AV2, and AVN. Now, when they are connected in cascade, the total gain, the overall gain will become overall gain will be equal to the product of the individual gain stages. So AVT will be AV1 into AV2 into AVN. Okay. And if the gain of the amplifier is calculated in dB, then the total overall voltage gain will be AV1 in dB plus AV2, right? Here I would have written over here. Let me edit it. This should be AV1. Yeah. So I've written over here AV1 in dB, AV2 in dB, and AVN in dB. Okay, so we have to add the voltage gains in dB and multiply them in the form of magnitude. So let's consider an example that over here, that let's say that for example, the first stage gain is around 100. Okay, and the second stage is providing a gain of 50. So what will be the overall gain now in a cascade amplifier? So overall, I mean, the total voltage gain will be equal to AV1 into AV2. And here we have AV1 as around 100 and AV2 is around 50. So what will be the total gain over here? The total gain over here will be 100 into 50. That will be 5,000. Now, such a high gain was not possible with a single stage amplifier. Now, that is only possible with a cascaded amplifier. That's why that's the advantage and that's the motivation for studying your cascaded amplifier. So, such a high gain. Now, this is a high value, high gain. Okay. So, this is only possible if we connect the amplifiers in a cascaded fashion, right? And that's the motivation to study the cascaded amplifier. Now, let's study something else now. Okay, let's understand the effect of cascading also affects the lower cutoff frequency, right? So again, if we consider a end stage cascaded amplifier, so let's say that if more than one amplifiers are cascaded, then the lower cutoff frequency FL increases and is equal to the highest FL in the cascaded chain. So let's look at the example. So let's say that if we have three amplifiers are connected in cascaded fashion, okay, in cascade with a frequency of 100 hertz, 30 hertz, and 20 hertz, then 100 hertz is the lower cutoff frequency of the cascaded stage. So just remember that. Okay. So if we have three stages whose lower cutoff frequency is 100, 30, and 20, then the cascade stage lower cutoff frequency will be the highest among the three, 100 hertz. Okay, so this is another concept. And now there is another one, that if n number of identical stages, now what do you mean by identical stages? Having similar gain are cascaded together with, identical stages in their DC parameters also, and with the same lower cutoff frequency. Let's say that all the three amplifiers connected in a cascade have a lower cutoff frequency of 100 hertz. Then how to calculate the lower cutoff frequency of a cascaded amplifier? So here we have written FL of cascade will be equal to FL divided by 2 raised to 1 upon n minus 1. Okay. So I think let's do a quick calculation over here also. So let's say that we have a lower cutoff frequency of a 3 So we consider an example 100 hertz. Okay, and number of stages are 3, so n will be 3, right? So we have want to find the lower cutoff frequency of of a cascaded stage, right? So we have three stages connected in cascade, right? So FL will be, FL of cascade will be, we can write it down. So lower cutoff frequency of a overall cascade stage will be equal to 100 hertz divided by, we can just write 100 divided by square root of twice into 1 by 3 minus 1. So this will be my lower cutoff frequency of my cascaded stage. So let's calculate that. So let's calculate 2 raised to 1 by 3 and let me do that. Yeah, minus 1 square root of that. So this will be 100 divided by 0.509. Okay, 8. Fine. So this will be equal to approximately 196. 196.15 hertz. So that will be the overall cutoff frequency of a overall lower cutoff frequency of a cascaded stage consisting of 3 identical stages having a lower cutoff frequency as 100 hertz. Okay, so the cascaded stage lower cutoff frequency will be around 196.15 hertz. Fine. So this was about the effect of cascading on the lower cutoff frequency. Now let's see an effect of cascading on the higher cutoff frequency, right? So let's just consider that when there are more than one amplifiers are cascaded, then the higher cutoff frequency FH of cascaded amplifier decreases. Now let's see how. Now, if you see carefully over here, let's say that this is my input stage and this is my output stage. Let's say we have used a BJT amplifier for that, and we have not drawn the complete one, but we have shown the interaction between the output of the first stage and the input of the second stage, right? So there are various capacitances associated, parasitic capacitances and wiring capacitances, right? So the output capacitances of the first amplifier will become, so CO1, that is the output parasitic capacitance of first stage, will become CO, right? Earlier it was, if it was not cascaded, then what would have been look like, right? So it would have been looked like this. So you have first stage, and the first stage overall, yeah. So it would have been CO, right? That's it. Output parasitic capacitances. But now since it is cascaded, now this would have been V out. Okay. Now this is first stage. This is single stage. This is single stage. And this over here is my cascade. So here the CO would have, the parasitic capacitance would have ended at CO itself. But now, since we have a second stage connection, so second stage will have a wiring capacitances. Second stage will have a Miller input capacitances associated. So CWI2, 2 stands for second stage, and CMI2 will also be added due to the cascading problem. Okay, and they are all connected in parallel, so that's why there is addition. So that means it will increase my output parasitic capacitances whenever we are connecting any amplifier in cascaded stage. So what it will do, in other words, the output shunt capacitance CO1 will increase. Definitely, if we are, if we are considering the second stage, so for the second stage, this is my additional capacitances which are present. Okay, which were not present before, right? For a single stage, they were not present, but these additional capacitances will increase my CO1, that is output parasitic capacitance. And you know that what is the higher cutoff frequency? It is given by 1 upon 2 pi R equivalent into CO1. Now, since CO1 is increasing, my higher cutoff frequency will decrease, if we are cascading two or more stages. Okay, so that's why we have said over here that when more than one amplifier are cascaded, the higher cutoff frequency FH of cascaded amplifier decreases. That's the reason for the decrease in the higher cutoff frequency. Okay, so this is one another important concept which you should remember. And another is that if n number of identical stages are cascaded together with same FH, then let's say that you have three stages, identical stages, which will have a higher cutoff frequency of, let's say, around 10 megahertz. Okay, then the higher cutoff frequency of a cascaded amplifier will be given by this formula. FH of cascade will be equal to FH. FH is the higher cutoff frequency of individual stage into square root of 2 raised to 1 upon n minus 1. So let's see an example over here. So for example, let's consider FH value of individual stage to be around 10 megahertz. Okay. So this is my higher cutoff frequency, 10 megahertz, and number of stages over here are, let's consider to be 3. So how do you calculate FH of the overall cascade stage? So FH of cascade will be equal to 10 mega, that is 10 into 10 raised to 6 into square root of 2 raised to 1 by 3 minus 1. Okay, so let's see that how it will be. So the higher cutoff frequency now, let's calculate again. So it will be like 10 into 10 raised to 6. Sorry for that. I should select eraser. Let me do that. Yeah. So now let me 10 into 10 raised to 6, 2 raised to 1 by 3 minus 1 the square root of. That value is around 0.5098. So if I multiply this with 10 megahertz, it will be around FH of a cascaded stage. Let me do that again. 0.5098 into 10 megahertz. So that will be 5.098 megahertz. So as you can see, the overall cutoff, overall higher cutoff frequency, if there are a similar identical stages cascaded together with the individual higher cutoff frequency of 10 megahertz, for a cascaded stage, it will reduce, right? So this is another important concept which you remember. Okay, so if we have three identical cascade stages having an individual higher cutoff frequency of around 10 megahertz, then the overall higher cutoff frequency will reduce, and it's reducing from 10 megahertz to 5.098 megahertz. Okay, so this is how the cascading will affect the higher cutoff frequency. So far we have seen how does the cascading affect the input and the output impedance, right? How to calculate the input impedance was the input resistance, what the input resistance of the first stage, and what we can say the output resistance was the output resistance of the last stage. Effect of cascading on the gain was increasing. Effect of cascading on the lower cutoff frequency was the lower cutoff frequency was increasing, and effect of cascading on the higher cutoff frequency was the higher cutoff frequency is reducing. So we have seen up till now the effect of cascading on these parameters. Lastly, we'll see the effect of cascading on the gain bandwidth product. So what is the gain bandwidth product? So gain bandwidth product for an amplifier is defined as that frequency at which the gain of the amplifier becomes unity, right? So the gain bandwidth product is given by AV mid into FH. Now we know that as we add the stages in cascade, the higher cutoff frequency will reduce. So therefore, AV mid will remain. AV mid will slightly increase also, right? So this product, mostly will, the gain bandwidth product. Since your FH is reducing, your gain bandwidth product will also reduce due to cascading. So with cascading, your lower cutoff frequency increases, your higher cutoff frequency reduces, and the bandwidth will also decrease, right? So if you cascade more and more stages, your bandwidth of your entire cascade stage will go on reducing, right? So that's the effect of cascading on the gain bandwidth product. Okay, fine. Let's move on to the next point. So there are various coupling schemes in a cascaded, amplifier. Now, what do you mean by coupling? Coupling means the way you connect the two stages together. Okay. So let's say this is my stage one and this is my stage two. So we can directly connect them with a wire. The output of first stage can be connected to the input of second stage directly with a wire. or we can connect it with a capacitor. So when we connect a capacitor, then the Q point of the first stage and the second stage will remain isolated. Okay, because we have a RC coupling over here. Here we have CC, and here we have the input resistance of the second stage. So this will form RC coupling, which will prevent the Q point of first stage to affect the Q point of the second stage. So coupling mechanism means how we connect the first stage to the second stage or the various stages in a cascade chain. Okay, so the coupling scheme will serve two purposes. It will transfer the AC output of one stage to the input of the next stage, as it is happening over here, right? So here, V out one contains the AC component, and that AC component becomes the input of the second stage. So that's how your AC travels from one stage to the other. Second condition is it might isolate. I mean, not always it will do that. In direct coupling, it will not isolate the DC condition. But the RC coupling will isolate the DC condition of one stage to the next. That means it will prevent the shifting of Q point between the two stages. Now, this point will be more clear when we'll solve numericals on the RC coupled amplifier, right? So let's see the type of coupling schemes. So there is a first type, that is RC coupling, right? So what do you mean by RC coupling? Amplifiers employing RC coupling are called as RC coupled amplifiers. Now let's say that you have a two-stage cascade. Okay, the amplifier one, stage one will have a gain of AV1, stage two will have a gain of AV2. We have applied input over here at the input of the first stage, and output is taken across the output of the second stage, and the load is there, right? So how are the first stage and the second stage connected? Via a coupling capacitor, and there is the input resistance of the second stage. So this forms a RC coupling. Okay, and amplifiers which employ RC coupling are called as RC coupled amplifiers. Okay, now let's see in more details over here, right? So here you see Q1 and Q2 will form the first stage and the second stage, and how they are connected together? The output of first stage over here is connected to the input of second stage via a coupling capacitor, and the input, we can see the input resistance of the second stage. Now, can you identify what will be the input resistance of the second stage over here, right? Let's just say that the values of these resistors are R2 and R3, right? So what will be the Ri of the second stage here? Okay, if you can tell, it will be R2 parallel to R3, and we have R pi also, right? So we can write R pi 2. So this will be the input impedance of the second stage, right? So this resistance and this capacitance together will form RC coupling, right? Now, what is the advantage of this RC coupling scheme? So let's study that next. So here the coupling capacitor CC and the input resistance of the next amplifier stage will form the coupling components, and it's the most common coupling scheme for a cascade amplifier. So what is the advantage? The advantage is that the DC biasing of individual stages will remain unchanged even after cascading. Now, what do you mean by DC biasing? The DC current and the voltage values of the first stage will remain undisturbed. So let's say that the first stage over here, we can describe more. The first stage will have a Q point, which is ICQ1, and we can have VCEQ1. So this will remain in complete isolation with ICQ2 and VCEQ2. Okay, so the Q point of the first stage will not disturb the Q point of the second stage because there is a RC coupling in between them. Okay, the capacitor, let's see a capacitor over here. Capacitor will block DC. Okay, so let me elaborate this point a little in more details, right? So since we have a capacitor over here, what's the property of a capacitor? Capacitor is supposed to block DC and allow AC to pass through it. Okay, so the capacitor will block DC and allow AC. So first stage will contain, the output of the first stage will contain DC plus AC component. Okay, so capacitor will allow, here we have AC plus DC, that capacitor will allow only AC to go through. Okay, that means the DC quantities, I mean the DC parameters, that is DC current and voltages will remain, first stage will remain isolated from the second stage. Okay, so that's the function of this RC coupling scheme. Fine, I hope it is clear. So the Q point of the first stage and the Q point of the second stage are completely isolated from one another. They remain undisturbed. Fine. So that's the advantage of RC coupling scheme. And if we have a RC coupling scheme, the disadvantage is that the voltage gain reduces at low frequency due to RC coupling, right? So what is this which you see in front of your screens? This is my, if I draw this, this is a frequency response of cascaded amplifier which employ RC coupling. So as you can see, at lower frequencies, the gain will fall down. And the reason for it is the RC coupling mechanism. Okay. And yeah, this is the bandwidth. So bandwidth of the RC coupled amplifiers is slightly lower as compared to the directly coupled amplifiers, right? So this is the disadvantage of RC coupling. Okay. Now let's see the next coupling mechanism, the direct coupling. So let's find out where it is. Yeah, here it is. So next coupling mechanism is directly coupling. Over here, the first stage is directly connected to the second stage with the help of a wire. Here it is, right? Now here, if you consider the DC over here, right? There is a DC quantity at the collector terminal over here. So here it contains DC plus AC, right? And here we have only DC. So this is the DC of the second stage. This is the DC of the first stage. Fine. So this AC plus DC will be directly passed on to the second stage, right? So AC will have no problem to flow, but the DC quantities or the DC parameters of the first stage will affect the DC parameters of the second stage. So that is the problem with the direct coupling, right? Direct coupling means connecting the output of the first stage to the input of the second stage with a wire. Okay. So your direct coupling will disturb the Q point of both the stages. Fine. So let's see that amplifiers employing the direct coupling scheme are called as directly coupled amplifiers. But these directly coupled amplifiers, advantage is that it used to amplify DC as well as very low frequency signals. Okay. So a directly coupled cascaded amplifier will have a frequency response which looks something like this. Okay. But the disadvantage is that the DC biasing conditions of the previous stage disturbs the DC biasing conditions of the next stage. So this is a disadvantage or a limitation. Okay. So you should be aware that, the direct coupling will have this disadvantage that your first stage DC conditions will affect the second stage DC conditions. Fine. So you have to take care of it. Yeah. So now let's proceed forward. Now over here, we will be doing a lot of analysis of amplifiers in the module number 2. So we have done so far in module number 1, DC analysis, mid-band analysis, low frequency analysis, and high frequency analysis, right? And we have done that with respect to this frequency response, right, of single stage amplifier. In a multi-stage or a cascade amplifier, we will have a similar kind of a frequency response for RC coupled amplifiers. So you will have a low frequency region where the gain will fall, the mid frequency region where the gain will remain almost constant, and the high frequency region where the gain will again fall. And the bandwidth of such amplifiers will be FH, the higher cutoff frequency, minus the lower cutoff frequency, right? So frequency response, y-axis is my voltage gain, and x-axis is the frequency in logarithmic scale, basically. Okay. So this is what we have done so far for the analysis of single stage amplifiers. Same as the analysis for the multi-stage or cascade amplifiers. Now, which type of cascade amplifiers we'll be studying in our curriculum? So we'll have common emitter, cascaded amplifier. Then we have common source, cascade amplifier, and we have common source, common emitter, cascade amplifier, right? Then we have common emitter, common base, cascade amplifier, and common source, common gate, cascade amplifier. So cascade amplifier is different than cascade amplifier. Cascade amplifier means one after the other. Okay. So you have one amplifier and you have a second amplifier connected. So one after the other. Okay. In case of Cascade, it is like stacking off. So you have one amplifier over here whose input is applied over here. And then we have a second amplifier at the top of the other, and here we'll have the output. Okay. So it's like one over the other, right? So this is the Cascade amplifier and this is the Cascade amplifier. Now Cascade amplifier will have certain advantages. So let's consider common emitter amplifier. So what features it will provide? So common emitter will provide a very high gain. That is the biggest feature of it, biggest advantage. It will provide very high gain. So let's just consider the first stage gain is around 100 and the second stage gain is around 50. Okay, we are talking about voltage gain. So what will be the overall voltage gain? 100 into 50, which is around 5000. This is just a number which I am taking, right? So the advantage of common emitter, cascaded stage will be very high gain. Now let's see the advantage of the common source. Let me just change the color to black. So the advantage will be of common source MOSFET amplifier, we can say. So here the advantage will be it will have very high input resistance. Okay, it won't provide that much high gain. So let's say the gain of first stage might be around 10 and the gain of second stage might be 5. So the voltage gain over here will be 10 into 5, that will be 50, which even a single stage amplifier provides a better gain. But what's the advantage over here? The advantage is that the first stage, since it is a common source, so Rn, the input resistance, will be equal to the input resistance of the first stage. And we know that for a MOSFET, the input resistance is very, very high. Okay, so that's why the input resistance of a common source cascade amplifier is very, very high. It offers very high input resistance. Okay, now the third category, the best one, is it's like a the advantage of both common emitter and common source are taken care of. So let's just consider this third case. So over here we have common source and common emitter. So let's say the gain over here, the gain of the common source amplifier is, let's say, around 10. And the gain of common emitter amplifier is around, let's say, 50. Okay, let's say a little bit more than that. First stage gain is around 5 and the second stage gain is around, let's say this is 5 and this is around 10. Let's just consider 10 only, 10 and 100, right? So what will be the gain of the overall stage now? So here the advantage is that it provides a high voltage gain. Okay, why high voltage gain? Because here AV will be 10 into 100, which is around 1000, which is a high gain. This is normally not obtained with the single stage amplifier. In addition to that, since we have connected the first stage as a common source, it will provide a high input resistance also. So both the features are important, because if we have a high input resistance, whatever source we connect at the input, it will not affect the amplifier. So the common emitter will provide two advantages. It will provide a high voltage gain. Along with it, it will provide a high input resistance. Now, all these things we will be covering in the numericals. When we'll cover the numericals, then we will understand why each of these cascaded amplifier configurations will have a unique advantage. Okay. Again, I repeat, common emitter will provide a very high gain. That's its feature. Common source cascade will provide a very high input resistance, and common emitter will provide a high voltage gain and high input resistance. Okay, so with this we have come to the end of this session, and we have covered the introduction to the cascading concept, and we have seen the effect of cascading on the voltage gain, input and output resistance. Then we have seen the effect of cascading on the lower cutoff frequency, higher cutoff frequency, and the gain bandwidth product, right? And also we have seen that what are the different types of coupling mechanisms. There were two types, RC coupling and direct coupling. And also we have seen that now that what are the types of cascade amplifiers we will analyze. And for all these cascade amplifiers, we have to do only two types of analysis. We have to, I mean, let me just write it down before we leave. So we have to find, I mean, we have to estimate for all these cascade amplifiers, we have to only do the DC analysis. I mean, DC analysis is there. So we have to do the DC analysis. Let me write over here what we have to do for cascaded amplifier. So for cascade stage, for cascade amplifier or cascade stages, let me just, yeah, we have to do the following. So number one, DC analysis. We have to know how to do the DC analysis of individual stages. Then we have to find the input resistance of the cascade stage. Next, we have to find the output resistance of the cascade stage. And then we have to find the overall voltage gain. I mean, if there is a two stage in a cascade, we have to find the individual voltage gain AV1, AV2, and then we have to find the overall voltage gain AVT. Okay, so these are the things which we have to find out. That's it. And for finding out AV1, AV2, and AVT, we have to also calculate the small signal parameters, right? So small signal parameters for BJT and MOSFET are different. So we have to do that. So this is what we have to do for a cascade stage, cascade amplifiers. Okay, similarly for the cascade amplifier also we have to do DC analysis. We have to find out Rin, we have to find out Rout, and the individual stage gain and the overall voltage gain. Okay, so that is all what we have to do. And yeah, we conclude this lecture now. And next time we'll start with the analysis of common emitter, RC coupled cascade amplifiers. Okay, so that's all for today. See you all next time.